So since we are aqueous based, it makes it more simple in some regards than it was in organic chemistry. So in vivo, for many parts, we're talking about only an aqueous environment. Now, what's one exception when it's not an aqueous environment? In vivo, that you'd have different types of properties that you would talk about. What part of your body is not going to be an aqueous environment? Yep, your skin, your lipids, ready? So any type of lipid bilayer, adipose tissue, it's going to be more hydrophobic, things like that. Then we're talking then we have to consider those reactions of that solvent, that localized solvent there. There are different types of reaction, or I should say interactions. Now we have those that are intermolecular, and so when I say intermolecular, it's just like the interstate, which means it's between more than one, like it's not within the compound, it's between the compounds. So we could talk, that could be an ion-ion interaction or even an ion-dipole interaction, okay? The way that potassium could be dissolved, potassium chloride or sodium chloride could be dissolved in water. So those are two different molecules coming together in the way that they interact, okay? Don't confuse this with intramolecular interaction. So many times people think, covalent versus non-covalent, but that's not what we're discussing here. Because many times it seems like people forget from Gen Chem to biochemistry, and we start doing reactions, and they just have things like atoms falling apart, and that's not going to happen, okay? So for the most part, unless there's an enzyme reaction or something going on, then it's not. You can dissolve something, then that's intramolecular reaction. So that could be two lipids or two fatty acids coming apart from each other, okay? But the individual atoms inside each of those fatty acids are not just disintegrating. All right, then we can also have dipole-dipole interactions. And that's where one polar moiety is dissolved into another polar moiety. So for example, alcohol here, in water. And then you can have induced, and you can also have an induced dipole with a dipole as well. And so induced usually are weaker, except for whenever we talk about really large molecules. So in our body, the only of the types of molecules here that would have really strong induced would be large chain fatty acids. So things like arachidonic acid, has a really arachidic acid, I should say, has a really low melting point because of the fact that it's bound to each other really tightly, and so that's why it can clog your arteries. Okay, so even at biological temperatures, it's stuck to itself because of the fact is that it's bound so tightly, and that's actually induced. Okay. All right. This is just, I would never ask you to memorize the numbers here, but just show the relative amounts of covalent versus non-covalent and how strong that they are. Ion-ion interactions are really strong. Of course, covalent themselves are going to be relatively strong, but it gets weaker and weaker in the intramolecular with respect to not having that dipole moment. Okay, so that's why hydrophobic or van der Waals interactions on a small scale is not very tight. Now, once you get really large molecules that are very hydrophobic, then they can start to exclude water, and their binding to each other can be very tight. Okay, so water, it's hydrophilic, which makes sense. Okay, so things that are polar will tend to dissolve in water. So that's why ethanol, alcohol, acetone, those will all dissolve in water. Salts. Hydrophobic things tend to not dissolve in water, so it's like oil. So that's why they separate out to form micelles and bicelles, and we'll talk about those in greater detail in chapters 11 and 12. And then we have what's called amphipathic, and the amphi means both, okay? And it means it loves both. And so typically, in the part that's important in vivo here, this is an example of palmitate, which is a fatty acid in your body, and it has a carboxylic acid on one end, which is going to be hydrophilic, and it's going to have a large hydrophobic chain. And so then the hydrophobic chains of neighboring palmitic acids will come together and get stuck. It will expose the hydrophilic portions, the head groups, So that's how, one of the reasons why that we have cell membranes that we do is because we have phospholipid bilayers that can spontaneously exclude water in their hydrophobic portion and yet interact with water at their head groups there. And so it's amphipathic. Okay. All right, then there's something special, and it's hydrogen bonding. And now, whenever I taught or teach Gen Chem, they have very rigid, and organic for that matter, they have very rigid definitions for hydrogen bonding. And biochemistry is much more less rigid in the sense that there are shades of gray. So what I mean by that is, for example, what are some of the atoms that can do hydrogen bonding? Besides hydrogen, obviously, has to be involved. But what are the other atoms that are involved in hydrogen bonding? Nitrogen. Whoops. Well, that did not come out well. Oxygen. Carbon does not do hydrogen bonding. Fluorine. Those are it. Which one of those is not going to be important in vivo? Fluorine. Okay, hydrofluoric acid is one that is hydrogen bonding, but we do not drink hydrofluoric acid. It's bad for you. But nitrogen and oxygen do. What must they have in order to hydrogen bond? Well, one has to have hydrogen. What does the reciprocal have to have? Lone pair electrons. Okay? And so it used to be in Gen Chem and organic that we really stressed the idea, so I'm going to draw an alcohol here. I don't know why this is not wanting to work. An alcohol, perhaps. We would even say that they had to have, to be reciprocal. So, for example, with water. So I did not draw this very well. It's not drawn to scale. But we can imagine that you have an interaction between the lone pair electrons of the oxygen with the hydrogen and this oxygen to hydrogen. Well, in biochemistry, many times, only one. So it doesn't have to be this tight reciprocal nature, alcohols with alcohols and amines with amines. And so what I mean by that, and I'll just show you an example. Oh, whoops, that's not what I meant to have happen. Is we could have, for example, an aldehyde. Or I'm going to make it a ketone so that way it's even hydrogen bonding to water, which, as I mentioned before, typically we wouldn't show this a lot in Gen Chem. We would say that it's not a very strong hydrogen bond. And granted, it's not as strong as like water to water in that sense. But you could have an interaction between the lone pair electrons of the oxygen with the hydrogen hanging off of the water. And so we see this a lot. And we're going to talk about in chapter 3 when we discuss, I think it's 3, when we start discussing amino acids and peptides and how they come together to make proteins. I mean, this is the major player behind that in the way that the proteins, or is a major player in the way that the proteins ultimately fold. All right. And so here, once again, it's just the fact that whenever you form dipole bond, hydrogen bonds are a special type of dipole bonds. They're a little bit stronger than a normal dipole bond, and especially if you can do that reciprocation. We will see some examples of that in vivo, but usually we're talking about things like aldehydes, ketones, carboxylic acids, amines with water or with each other. Right? Here we go. Okay. Oh, and this just shows as an example here, which I usually do point out in both Gen Chem and briefly in organic, that once again, we have to take size into account because size does matter. So if we take things that are roughly the same size, so here the molecular weight of ammonia, water, and methane are all approximately equal, but they have very, very different melting points and boiling points. Now, in organic chemistry, we usually used boiling point a lot of times to talk about how stable something was. The higher the boiling point, the more stable. We don't talk about that very much in biochemistry. Does anyone want to venture a guess why we don't discuss boiling points, that we use melting points instead? would we use melting point versus boiling point a lot of times when we talk about stability?
Too extreme for our body.
Right. It's not like we're going to get hot enough in order for it to boil. Whereas we can, I mean, it is biologically relevant to have your lipids. Just think about, I don't know if any of you cook with coconut oil, but coconut oil, you just set it out on this shelf and it's not very warm. It starts to solidify. You put that in your body, of course, it's going to be a liquid because it's 37 degrees Celsius instead of 23 degrees. So that's why it's much more pertinent to discuss melting points and boiling points, which I wouldn't even know what that is, but it would be really high for that. And so, but the reason why that this trend we see is that methane cannot do any hydrogen bonding. Ammonia can hydrogen bond, but the oxygen in water hydrogen bonds even better than nitrogen because it's even more electronegative. Remember, the closer you get to fluorine, the more electronegative it is. Fluorine is the most electronegative. Oxygen is a close second, then followed by chlorine and nitrogen. Okay. Right, so this is just an example showing everything that this would let me just do a little. This one unfortunately doesn't do a little highlighter. It always wants to mark everything. But here we have water with an alcohol. We have it with the aldehyde or the ketone. We can have between nitrogens and the alcohols, nitrogens and the carbonyl groups, which this is the one that's so important. This one right here. So important for proteins and also for nucleic acids, but especially for proteins. And then we see this kind down here below many times nucleic acids, especially RNA. Okay, you can also with DNA. All right, acids and bases. So we keep this relatively simple here. Strong acid or strong base means it completely dissolves in water. We don't use these in vivo. Why would we not use these in vivo? They'd be very dangerous. Now, that being said, I say that we don't use these, and we do use H3O+, which if you remember, if you took organic chemistry with me, which a lot of times we just write that as a generic acid. So H3O+, the hydronium ion, is important. And hydroxide itself is important too, but it's usually attached along with a metal, such as, or like chelated to a metal, held in place by a metal, so where it's not just going, willy-nilly all over the place, because then it can be bad. And so once in a while you'll hear it talk about a general base attack, and that is a hydroxide. But almost always, once again, it's held in place by a metal, or it's even a water that a metal comes close enough to that it takes off something takes off one of the hydrogen, so it can act like hydroxide. But you do not eat sodium hydroxide or lithium hydroxide. You do magnesium hydroxide. I mean, that's milk of magnesia. But a lot of these you wouldn't. Okay. Usually, 99% of the time, we're talking about weak acids and weak bases. And that just means it doesn't completely dissolve in vivo. Okay, it will not completely dissolve in your body. So instead of being 100%, maybe it's 90, maybe it's 50-50. Sometimes we're talking about as little as like 3 to 5% is all that you need to be dissolved, to have deprotonated. Okay, when I say dissolved, I mean by deprotonation. Okay. An acid will become a conjugate base, and a base will become a conjugate acid, and vice versa. And it is interchangeable in the sense that it really depends on if we're talking about this going this direction, or since it's in vivo, usually we're talking about things that are reversible. So it could be going either direction. And so that's why the acid on one side will be the conjugate base on the other, and vice versa. And so at this point in time, I would expect you to be able to pick out in a reaction what the acid was, what was the base, what the conjugate acid, which conjugate base is. Just look to see how many hydrogens is on each of them, because whatever's losing a hydrogen has to be an acid, and whatever's gaining it would be a base. Okay. And that's the simplest Bronsted-Lowry definition, because there are something called Lewis acids and bases, which has to do with electrons and not. Okay. you don't have to memorize this. This just actually shows you how you get the term pH. I'm sorry, pH 7 being neutral, because it's just the product association for water. And if you do this under normal conditions, water comes out with a Kw, which is an equilibrium constant of 1 times 10 to the minus 14. So that means the hydrogens have to be 1 times 10 to the minus 7, and the hydroxides have to be 1 times 10 to the minus 7. Okay, and so that's where we ultimately get pH. But what I'm going to focus on here is I want to talk a little bit more about Ka. And actually, I think I'm just going to draw it out. Okay, so let me make this skinnier. We have our generic acid. Now, in vivo, that H plus is almost always going to be H3O plus. I'm just going to be drawing it as H plus, so that way it's easier for me to write every time. But remember, we have water around, and so it's going to be H3O plus. Right. Or it's going to be, you know, a nitrogen coming and taking it, so it's not an ammonium cation. Okay, so it's not as free hydrogens floating around, even though many times you draw it that way. By definition, we're looking at a special equilibrium constant. So that's the acid equilibrium constant. And by definition, all equilibrium constants, what's the generic, what goes on top? Say it was some products. It's always products over reactants. And so, even though I'm going to warn you right now, my brackets, these are concentrations. They're going to look more and more like parentheses by the end of this, just because I get going fast. So we have our products. When we're talking about dissociation, it's the products there, and the reactant is the conjugate, or the original acid here. No, I don't want to circle it. It's like a delay today. Okay. Now I'm going to do something here that's just a little, it's just to help in a moment with the math. And I'm going to factor out the hydrogen. So that's the same thing. We can say that's the same thing as saying H plus times A minus over HA. Okay, whoops, and in parentheses. It's the same thing. You multiply that, you're going to get the original thing, which is Ka. Because without skipping any steps, now we're going to do, remember from algebra, whatever you do to the left side, you have to do to the right side. It doesn't really matter. It's going to be true as long as you do the exact same thing to both sides. So let's take the log of those. So we're going to have the log, perhaps we'll have the log of Ka is equal to, and what is true whenever you do the rule of logs, when you multiply things? You add them. Okay, so that means log of hydrogen plus the log of everything that was in the parentheses. Okay. The reason why we do this is usually these equilibrium constants, just like that last slide, we were talking about 1 times 10 to the negative 14. You do not want to have to write out 0.0000000000014. I'm sure that wasn't right. Whatever. But something, yes?
Will we be able to do the log of the other one, even though they're equal? Will we get the same?
Yes, yeah. So, yes, all of that is true so far. We took the log of one side is going to equal the log of the other side. And so all that across the top is equal to itself. But we do this because the whole idea is you want to make sure that anything that you have is more manageable. So this is, I'm ultimately coming up to where we get the term pH. So you normally use, so what's neutral pH? 7. And so see, 7 is a lot easier to talk about than 1 times 10 to the negative 7. Okay. And so that's why we have to mathematically use a new function. And so what we're going to do now is we're going to take times everything by negative 1. Okay, and I assume you have this written down. I've run out of room on this. I'm going to have to get me a new thing. So if I multiply everything by negative 1, it's going to look like this. Negative log Ka is equal to the negative log of H plus, okay, minus the log, that's supposed to say log, what's log? Let me see if I can, and right now we're talking about log base 10 of A minus over HA. Okay, now I'm not going to skip any steps whatsoever here. All I'm going to do is, you see this entire, let me just put a circle around it, this really large cumbersome looking thing, we're just going to move it and add it to the other side. Okay, so since it's negative one side, if you add a negative log of that to one side, you have to do it to the other side. Okay, so we're going to move it on over. So we now have negative log K. I don't know why this is not wanting to write. Ka plus the log of A minus over HA. Okay, is equal to negative log of H. So far, that doesn't look pretty. But in math, there is a function, and I actually don't know what the real function's name is. It probably has a really cool name, but it's the P function. Okay, and so that's where we actually get the idea of pH. That little P, which here, let me change the color so that way you can draw it out here. When I say P, it's a lowercase p. And what that does is that's equal to negative log base 10 of something. Okay, and we do that because now this negative log of H plus becomes pH. Every time you see that little p, whether it's pH, pKa, pi, POH, that just means negative log base 10 of whatever follows the p. So since that is equal to pH, that negative log of Ka becomes pKa. And in biochemistry, those are two very, very important terms, pH and pKa. Now, we don't do anything with it. We just leave it the ugly plus log of all of that jazz. Okay. So plus the log of A minus over HA. This right here has a special name, and it's one that you learn all the way back in Gen Chem. We also cover in organic, now we're covering again, so therefore it must be important. That's called the Henderson-Hasselbalch. Oh, that's really thick. Okay. Henderson-Hasselbalch equation. And that's very important. We use it whenever we would talk about buffer systems. They use it with respect to medicine and medicinal chemistry. Okay. We use it in vivo whenever we're trying to determine like the likelihood of something being in one form or the other. So pKa is a constant that is indicative of whatever molecule that we're looking at. It just means it's a molecule that has a hydrogen that can come on and off. And pH, of course, is pH. It's a concentration of the hydrogens that are around, which in neutral, it's pH is 7. But what is the approximate pH of blood? Does anyone remember? Is your blood slightly acidic, basic, or is it perfectly neutral? It's a little basic. It's like 7.4, 7.41. Whereas parts of your cell are like pH 5. Okay, and so your stomach, pH 1, roughly. And that's why there are differences. So something that can be ionized in one part of your body can become deionized later on, or unionized, which is important in medicine. That's the reason why some of your medicines, you take it, it doesn't affect your stomach at all because it's not, it's ionized correctly. And so therefore, once it gets to your intestines where the pH is different, then it becomes unionized and it can pass through the lipid membrane layer. And if you go on to take medicinal chemistry, we talk about that kind of stuff all the time. Okay, but this is the Henderson-Hasselbalch. The thing that I want to point out here, the last one thing I want to point out is this A- is just the conjugate base of whatever, okay? The HA is a conjugate acid. So that's why, I didn't bring it with me, is if we go back, I'll probably go forward a little ways. So here we can actually do, pyruvic acid, the one at the top, may not sound like it's very important, but in your body that's actually really important because pyruvic acid, that's a carboxylic acid, what's the ending on a carboxylic acid whenever it loses its hydrogen? 8. Okay, it's either O8 or 8 depending upon it. And this one becomes pyruvate. And does anyone know what pyruvate, why it's so important? Actually it's important for multiple things, but what's one reason that it's important? Especially if you've already taken the MCAT, I'm sure that I would not be surprised if there's something on there in one form or another that had to do with pyruvate, either directly or indirectly. Does anyone know what metabolic pathway it's important for? It's glycolysis. It's the final product, the immediate product of glycolysis in step 10 is pyruvate. Okay, it also, by the way, this helps with alanine metabolism. It's involved in, it's a feeder pathway for the citric acid pathway. It can be useful for certain neurotransmitters and things like that, but protein metabolism, so on and so forth. But yeah, so that's why it may not look like, we went through all this and it didn't really matter, but it does matter because pyruvate in of itself is a buffer system, so it has a conjugate acid and a conjugate base. All of the amino acids are a buffer system of themselves because by their very nature they have both an amino group, they also have a carboxylic acid group, and some of them have even other groups on them that have hydrogens that come on and off. So that means every amino acid has to have at least 2 pKa's. One for the amino end, one for the carboxylic acid end. Some of them have a third pKa because their R group also has a hydrogen that can come on and off. Now, as I mentioned before, you want to start memorizing your amino acids. You need to know their structure, their name, 1-letter and 3-letter codes. I don't have the date with me because I didn't bring the calendar with me, but it's towards the end of September, like that 20-something of September. So probably in a couple weeks. That'll be your first quiz that you'll have an amino acid structure on there. And from then on out, every single quiz and exam has something about amino acids, and that's not just true for Biochem 1, but it's also true for Biochem 2. Okay, so I'm going to go ahead